So, we know now that the derivative of the natural log of x is 1 over x. As an exercise, let's find the derivative of the natural log of f of x, where f may be any differentiable function. Of course, this is as usual a composite function. We are composing first f with the natural log. So we will have to start differentiating the natural log, and according to the formula up there, we have 1 over, it will be 1 over the argument, which is now f of x. This part takes care of the natural log. Now, chain rule, we need to multiply by the derivative of what is inside, which is f, and so I get f prime of x. We can then combine this expression in a single fraction, and we get this nice formula. For instance, let's find the derivative of the natural log of x squared plus 4x minus 7. So this is basically my f of x now. So other than applying the chain rule, I can actually use directly the formula here. And what I get is fraction, the derivative of f, which would be 2x plus 4, divided by f of x, which is x squared plus 4x minus 7. We're actually applying the chain rule, but in some sense we are cutting corners, so we get the final answer in a much faster way. This formula also turns out to be quite helpful if we multiply both sides by f of x, so that we can actually cancel f out here. So if we read from the right to the left, what we have is f prime of x equal to f of x times the derivative of the natural log of f of x. This is the formula for the so-called logarithmic differentiation. In practice, this formula allows you to determine the derivative of f once you know the derivative of the natural log of f. Well, in general, the natural log of f is a worse function than f is, so you don't want to find the derivative of the log of f for the sake of computing the derivative of f. But in some cases, it turns out that the log f is more manageable than f itself. And the main reason is that logarithms are not so great looking functions, but they have nice algebraic properties. For instance, we can handle the natural log of a product as the sum of two natural logs. Also, we have properties with exponents, and so these properties sometimes may help simplify your function. So, for instance, suppose we need to find the derivative of the following function. Well, you see, overall, this function is a quotient. So we should first start using the quotient rule. So we need to find the derivative of the numerator times the denominator as is minus the numerator as is times the derivative of the denominator. When we need to find the derivative of the numerator, that's already another product rule. And there is also a square, so there is also a chain rule inside. So it is doable, but it will probably take at least a half an hour. This is where logarithmic differentiation may help. When you have quotients and products, it may be that applying the logarithmic differentiation formula simplifies a lot your computations. So let's recall the logarithmic differentiation formula. To find the derivative of f, we just need to multiply f as is by the derivative of the natural log of f of x. So I just need to write f as is times the derivative of the natural log of the same expression. Before we start differentiating, we want to work a little bit with properties of logarithms. Here we have a product and a quotient. So when you have the product in terms of logarithms, we can decompose as the sum of the two logarithms. And when you have the quotient, you can actually have the difference. So we can rewrite as the derivative of the natural log of x plus 1 squared plus the natural log of 2x squared minus 3 minus the natural log of the square root of x squared plus 1. We can do even better. We have a formula for logarithms that allows us to bring the 2 in front. And this square root, if you think of that as to the half, will also allow you to bring the half in front. So that we get the following. Again, f of x, the derivative of 2 log of x plus 1 plus log of 2x squared minus 3 minus half the log of x squared plus 1. So you see, all fractions, squares, square roots just vanish. And this is because of the good properties of logarithms. We can now find the derivative of every single log here, and we will basically done. So again, f times the derivative of 2 natural log of x plus 1. So we can use the fact that the natural log of f as a derivative, if you remember, has f prime over f. So in this case, what I get is the derivative of this, which is 1 over f itself, which is x plus 1. Don't forget the 2 in front, okay? Now here, same story. Down here f, up here the derivative. Negative 1 in front, same story here. X squared plus 1 here, 2x here. We can now try to improve a little bit the form, not much. And we get 2 over x plus 1 plus 4x over 2x squared minus 3 can cancel 2 and 2, so minus x over x squared plus 1. Logarithmic differentiation is actually the only option you have when you need to find the derivative of a function in the form of function f of x to another function g of x. That is, when x occurs both on the base and the exponent. Simple example would be the function x to the x, or x to the sine of x, or sine of x to the cosine of x. All these are examples in the form f to the g of x. So we cannot use the power rule, since the exponent is not a number. We cannot use any of the formula we have seen except logarithmic differentiation. So the idea is the following. The derivative of this function according to logarithmic differentiation will be the function itself multiplied by the derivative of the natural log of the function. And again, we use logarithm properties to bring g of x in front, so that we get, again, f of x to the g of x times the derivative of g of x natural log of f of x. And this now is just a product of two functions, so the product rule will do the job. For instance, let's find the derivative of the function x to the x. As we said, we want to use logarithmic differentiation, so that will be the function as is times the derivative of the natural log of the function. And again, the idea is this x will move in front. So we have x to the x, the derivative of x natural log of x. And here we are going to use the product rule. So x to the x times derivative of the first term, which is 1, times the natural log of x, plus the first term as is, times the derivative of the second term, which is, I hope you remember, 1 over x. So we can now simplify things a little bit. We have the natural log of x, and here we cancel x and x, and we get 1.